Hi, so this is a quick refresher video on resistance and capacitance in electricity. Now you'll remember, I'm sure, that if I connect a resistor up to a battery, so that's the battery, there's the resistor up there, with a resistance R and a voltage V, I will find out a current flowing around the circuit. Now you can do an experiment where you can measure the current as a function of the voltage at a fixed resistance, and you find that you get this straight line. Alright? This is for your common garden resistor that you can buy in Radio Shack. Now we define the slope of this to be 1 over R. Of course, this is Ohm's law, the famous Ohm's law, and the relationship is just that the voltage equals the current times the resistance. Okay, there's nothing special about this, it's just empirically determined. Now I can do a similar thing with capacitors. So if I take a capacitor now instead of a resistor, and again connect it up to a battery. Now what happens if I switch this circuit on? Okay, just let me remind you, V is the voltage and C now is the capacitance. If I switch this on, I'll initially get a current flowing through this circuit, but then this current diminishes as the capacity charges up with charge Q. So at the end of the experiment, I'll find an amount Q charge on the capacitor, but the voltage will be at 0. So I can do many different experiments. I can change the voltage and see how much charge accumulates on the capacitor. So if I plot the charge Q against the voltage, I will again find a straight line. This time the slope is the capacitance. So I can now write down this relationship. The voltage equals, the charge equals the capacitance times the voltage. So these two relationships are very important. Right? Now I can go further with the capacitance relationship. If I were to differentiate both sides with respect to time, I will get dq by dt. Right? And if I assume that the capacitance is not a function of time, so that's fixed, and then I can differentiate the voltage with respect to time as well. Now this thing here is the current. The rate of change of the charge is the current. So I can rewrite this down as current equals C times dV by dt. Okay? So this also is a very important relationship and one you'll need to use in your exercises. Now the other thing I want to briefly mention are the laws concerning networks of capacitors and resistors. I'm sure you'll all remember that if I have a series of resistors, let's just put 2, but I could have as many as I like, with a battery there, so there's a battery with a voltage V, resistance 1, resistance 2. The total resistance of this circuit is the sum of the two resistors. Okay, I'm sure you remember that rule. Likewise, if I had two resistors in parallel instead of in series, okay, with resistance R1, resistance R2, the overall resistance of this odd looking equation, 1 over R is 1 over R1 plus 1 over R2. Okay, so you probably remember that for your basic electricity. Now we have something slightly different when we come to capacitors. In fact, we have the opposite rule. So if I have, let me use a different color. If I have, say, two capacitors in series like this, connected to a battery, say C1 and C2. This time the overall capacitance is 1 over C equals 1 over C1 plus 1 over C2. And the simpler relationship applies to the network where the capacitors are in parallel. So if I put them in parallel, okay, the overall capacitance here, C, is C1 plus C2. Okay. And finally, Kirchhoff's current law, if I were to have a number of wires coming into a point and a wire coming out, that's current I1, current I2, current I3, 3. Kirchhoff's current law tells me that the amount of current coming out is the amount of current, total amount of current coming in. Okay, so that summarizes some of the basic ideas in electricity. Okay.